In the previous video, we looked at 3 different algorithms for traversing a binary tree, namely pre-order, in-order, and post-order traversal algorithms. Just a quick reminder, in the pre-order traversal, the idea is that you start from the root node, you process the current node, which is the root node first. Now, as I said, process in this example is just printing the key on the screen, but it can be changing it or searching for a specific value, you name it. But the idea is the order is first you start from the root node, you process that, you shout it out, and then you recursively call your algorithm on the entire left subtree, and you go to the right subtree only when you are completely done with the left subtree. So after 10, you go to the right subtree and start over from the root of that left subtree, which is this node here. And again, because this is pre-order, you first shout out 2, and then go to the left subtree. Make a recursive call on the left subtree. The root is 7, you shout out 7, then you go left, which is the subtree that has only 5 in it, you shout out 5. Then you try to go to the left subtree, but it's empty. That's the base case. You don't do anything, you just return. And after the left subtree, you go to the right subtree, and that's also empty, so you return without printing anything. And now that we are completely done with the left subtree of this tree here with 3 nodes, we process the root, we process the left subtree, then it's time to go to the right subtree, and we shout out 12. And again, now we are done completely with this subtree that is circled in green. And when you are done with the root and the left subtree, it's time to go to the right subtree to shout out 8 and so on. So this is called pre-order. Now, if we change the order of current node, left subtree, and right subtree, we get the other 2 algorithms. So in order means first you process all the nodes in the left subtree, then the root, and then the right subtree. So left, shout out the current node, and then right. So recursive call, and then you process the current node, and then make another recursive call on the right subtree. And finally, post order is left, right, and then the current. So these were the 3 algorithms, and we did examples of this. Now, in this video, what I'm going to do is, first of all, I want to show the connection between these 3 algorithms and the what's called prefix, postfix, and infix notation in arithmetic. And also, I want to show you the pseudocode for these 3 traversal algorithms. And in the next video, we will actually implement them in C++. Okay, so here's an example to show how this idea of pre-order, post-order, and in-order traversal relates to prefix, postfix, and infix notation in arithmetic. Okay, so if you remember, we said that one of the applications of binary trees is we can represent text in this form, and that shows the inner structure of that linear text that can be, in this case, an arithmetic expression more clearly. So imagine that we have this binary tree that has plus on the top, and then multiplication on the left, and subtraction on the right. And then multiplication, the left operand of this multiplication is the constant 5. And then on the right side, we have another binary operator, division. And then division has the number 4 as its left operand and the constant 2 as the right operand. And then for minus, we have the constant on the left, namely 7, and the constant on the right, let's say 3. Okay, so this is a binary tree representing an arithmetic expression. Now, if we traverse this in Infix, using Infix, I'm sorry, in order traversal. Okay, so I will traverse this binary tree using in order traversal. Okay, let's see what we get. So in order says go to the left first, and then go left again. And at 5, we try to go left, there is no left, then we print 5, and then we try to go right, but there is no right, so we are done with the left subtree of this tree rooted at the star. So now that we are done with the left subtree, it's the root's turn, so star, and then you go to the right, and the root is this division root, but first we do left, so we have 4, and then after the left we have the root itself, which is division, and then after that we go to the right 2. Okay, now looking at this subtree that is rooted with a star, we have finished the left subtree, we have finished the root, and we have finished the right subtree, which means that we are done completely with the left subtree of the entire binary tree. So after finishing the left subtree, it's time for the root, so plus, and then we go right. So now we are dealing with this subtree here with subtraction 7 and 3. First we go to the left, so we have 7, and then we have the root minus, and finally 3. Now, if I want to parenthesize this, this is what's going on here. So we have 4 divided by 2, and then 5 times that, 7 minus 3, and finally this entire, right? And this is what we call infix notation for in arithmetic, because the operations are in between the two operands, right? 4 and 2 are being divided. The division symbol is in between. 5 is being multiplied by this expression. So the multiplication is between 5 and the other operand that is being multiplied by 5, and so on and so forth. So infix in order. Now, similarly, if I use pre-order traversal, algorithm. So it means root first, then the entire left subtree, then the right subtree. What we end up with is we say plus, and then we go to the left subtree, root that star. First we do the root, so times, and then we go left, 5. Then we go right, we have division, and then we have 4 and 2. Now we are done completely with the left subtree, so we go right. We first write the root, then the left, and then the right subtree. Now, in this notation, which, believe it or not, it's much easier to work with in terms of, if you're implementing arithmetic in a programming language. In this notation, which is called the prefix notation, the operation is before the two operands. So, for example, here you have 7 and 3, so minus comes before that. So if you want to fully parenthesize this again, so this is what's going on here, right? So the subtraction of 7 and 3, so 7 minus 3, as we are used to, and so on and so forth, right? Division 4, 2, so that's 4 divided by 2, and then multiplication of 5 and this, so something like this, right? So divide 4 by 2, and then multiply 5 by that. And then finally, the addition of this expression and this expression is the entire. Okay, so as I said, this is called the prefix notation, which has its own advantages in comparison. I mean, we are more used to infix notation in mathematics, but if you are implementing these, prefix is much easier to parse. Now, the final thing for today, for this video, that I want to talk about in terms of these three traversal algorithms is their pseudocode, which turns out to be very simple. Now, the emphasis here is on pseudocode because these are not C++ code, but we will see that in the next video. So let's start with pre-order. And let's say that we just want to print the keys in a tree. Okay, so we have pre-order, and the input is a tree called tree, a binary tree, right? Now, it's going to be a recursive function, a recursive algorithm. So we need a base case. And the base case, if you remember from the example, I said this over and over, that if your tree is empty, then you don't need to do anything in terms of traversing it. So if tree is empty, then just return. And that would be the end. Return. Okay. Now, otherwise, what we do in pre-order is first we print the current node's data. So tree.data. Okay. So that's processing the current node. Processing here means just printing the data in that node. And then we have to go to the left subtree. So that's going to be a recursive call. So I call pre-order on the left. So tree.left. Left. And then make another recursive call. My pen is acting out again on the right subtree. Tree.right. And that's it. Okay. So if it's empty, just return. That's the base case. And if not, first process the current node. So this is the base case. And these are the recursive calls. Recursive call. Yeah. So if it's empty, just return. Don't do anything. Otherwise, first print the data in the current node, and then make a recursive call to the left subtree, and make a recursive call to on the right subtree, and that will be it. Now, obviously in C++, the syntax is going to be different. In particular, since we are going to use pointers instead of dot, you're going to use arrow, and so on and so forth, but you get the idea, right? Now, the other two, post order and in order, are going to be very similar. I'm not going to write them down because in the next video, we are going to actually implement them. But obviously, it's going to be in order or post order. And the only thing different is where you make the recursive calls in comparison to printing the data. So if you put print data in between the two recursive calls, then it's in order. So in order here, in order, and then put the print in between. That's the pseudocode for in order traversal. And if you put the print statement, the processing of the current node, last between these three lines, then what you have is post order. So post order here, base case is the same. Then you say post order tree.left, post order tree.right, and then you put the print statement at the bottom. And that's your post order traversal. As I said, in the next video, we are going to implement these three functions. We are going to implement binary trees first in C++ as a class, and then as members of that class, we are going to implement the traversal algorithms and also a couple of other functions for computing, say the height of the tree, which we talked about in the previous video, the size of the tree, which is the number of nodes in it, and maybe one more member function called left.